Hello everyone. I thought we'd go over some equilibrium questions, as some students seem to have some questions about that, so I thought I'd make a little video to post on YouTube about this. This is going to be going over the Exam 3 study guide. We're specifically going to be looking at questions starting at 7 in the equilibrium section. This is really how reversible reactions try and stay balanced. We mentioned that every reversible reaction has its own unique balance point. And so this little section in this video is going to help you understand how atoms flow between the reactants and the products based on achieving that balance point, their equilibrium between those two. So in the first problem, we set up a hypothetical reaction. At this point, we don't even get into dealing with specific chemical entities. We just say in a hypothetical reaction, let's assume that A is in a reversible reaction with B. So A kind of forms B, but then sometimes B can react to form A. It goes back and forth constantly. And so in this equilibrium, the reversible reaction is considered in its own balance when there is twice as much A. So here I kind of have a hypothetical bucket, kind of showing that we have twice as many beads of A than there are of the product B here. So when this reaction has achieved equilibrium, there's about twice as much A as there is B here. And we're going to use this to answer some questions. So the first question we have is, what direction would the reaction move if additional compound A is added? So here we're going to be perturbing the system in a sense, or messing things up. It's achieved balance, harmonious union type of situation, and now we're going to mess it up. Okay, so we got some more beads here. Let's just say we just add a bunch over here. Not really going to take the time to try and get this all balanced up here to achieve these values. Now we can see that the reaction is out of balance. We've added a lot more A than there is B here. So what's going to happen is some of these beads now, these chemicals, are going to move over to the other side to try and re-achieve balance here. So now we'd have a situation where some of the stuff moved from this side over across to this side. So that makes stuff moving to the right direction. As we're kind of thinking about things move to the right side of this chemical reaction. And so some of what was originally A converted over to B to re-achieve that balance. So that's the type of logic that we're going to be using here. Let's set up the problem just like it was beforehand. So I think we had 6 on that side, and then I had 12 on this side. Perfect. Alright, so and then an 8, what direction would the reaction move if some of A was removed? Alright, so let's just get rid of half of A initially here. So let's say now we mess the system up. Could you guys make a prediction on what reaction or what direction you think these reactants would flow? Would some of this go to make more of this, B, or would some of this move over to the side to make more of A? Well, with these reactions, its own balance point is that it always wants to form a 2-to-1 ratio, so twice as much A as there is to B. So what's going to happen here is that we're going to have some of this move over to form some of this. Maybe the numbers don't work out super perfect based on just what I initially grabbed, but it tries to get more into balance. So things would flow to the left side here. Great. So sometimes we can ask you not just questions about how atoms are flowing, but also who is being created or destroyed in this process. As anytime we have this net flow of atoms, technically we're creating more of one thing at the expense of another. Just like if we have money in our bank account, if we transfer money of our bank account to someone else, technically someone is gaining and someone is losing money. Okay, so in 9 here we state what would happen if you decrease molecule A. So we put the reaction back to how it was initially, just for convenience. So we have twice as much A as there is B. What would happen if we decrease A? So let's say we get rid of just this top row. We get rid of a little bit of A. So now the system's not in complete balance because it wants to be 2 to 1. A to B. So now the amount, we have two choices. The amount of B would increase, meaning we'd have to make more of this, or the amount of B would decrease. Well, because now there's too much B as there is for A, because we got rid of some of this, some of B is going to try and flow over and recreate a balance here. So we have, what, 10 here and 5 here? So perfect. That worked out pretty well based on me just grabbing random ones here. So now the situation, this reaction would be back in balance. So if we got rid of some of A, some of B has to flow back over to compensate. Okay, and then we'll do the last, we'll maybe skip 10 right now, and then move into the more complex situation of starting with problems after 11. So here we move to the reaction that controls the pH of our blood. And in this, there are actually 3 different buckets in a sense, because there are 2 reactions connected. So we're going to throw in a third bucket. Whoa. And we're going to put in, fill them up, because there wants to be some balance point. We don't give you any specific information on what the relative ratios are. So just for ease of convenience, we're going to make it so there are 6 beads, 6 beads, and 6 beads. So we're going to say that this first bucket here represents carbon dioxide with water, and then there's a reaction arrow between this stuff and then the product it can form, that H2CO3. Although you don't need to know that for the exam, its name is carbonic acid. And then carbonic acid can separate out and give out its free proton, so there'd be a reaction arrow here, to the third and final bucket where you have H plus goes to separated by itself. Okay, so now we can think about these 3 buckets. They're all connected, and atoms can flow across from this bucket to that bucket, and atoms can flow from this one to that one, and vice versa, to achieve a balance here. So now in question 11, we ask what would happen if more H plus were added to the system. So first we have to figure out what bucket has H plus. That's technically the last one. So here we have a lot of H plus. So we could throw in, we're just going to randomly throw in 3 beads here. Okay, so now the system's out of balance. So it wanted to be an equal number in buckets 1, 2, and 3. And now this third bucket, the H, has the H plus in it, the free proton, has too much stuff. So basically what's going to happen is things are going to try to flow across to achieve balance here. So here the reaction would go towards the left-hand side to try and achieve a balance. So maybe we'd have some stuff go over here. So now it's a little bit more balanced. There's some more stuff here, but there's less because some of the beads flew over here. So the reaction went to the left to try and achieve a little bit more balance. But now we can see this is out of balance, right? There's a little too much here than there is here. So this basically creates this chain reaction, or like this cascade process, where now we're going to have one of these products move over here. So now we initially added stuff over here, that balanced out by some of the atoms flowing to the left into this bucket. Then there was too much stuff over here, so some of the atoms had to flow over into this bucket. So now we end up with a situation where we have 7 beads, 7 beads, and 7 beads. So we've achieved harmonious balance. Alright, so let's set up the system just as it was, 6 beads in each bucket. Perfect. So now in 12, what would happen if more carbon dioxide, CO2, was added to the system? Okay, so we have to figure out what bucket CO2 happens when we think about this bucket analogy. By the way, you don't have to always recreate this in your heads, but I found that this bucket analogy worked out really well to visualize what's going on. When I just tried to look at the reaction, sometimes I would get confused, and so this is a really helpful analogy here. Okay, so let's say we add more CO2. Let's do the same thing. Just dump in a bunch more CO2 over here. So now this first bucket has a lot more stuff into it. And these two have initially they initially had, but technically it's out of balance because there's too much over here, not enough over here. So we're going to have some atoms flow from CO2, the first bucket, into the carbonic acid, the second bucket. So it's a little bit more balanced. And then because this bucket has a little bit more than this, reactions are again going to flow, our atoms are going to flow to the left, or to the right. I'm sorry, I'm doing this backwards relative to the camera, and so it's a little hard. Stage left versus stage right, I guess. And they're going to flow to the right. So now we got 7, 7, and 7. So technically, when we made more CO2, it's caused everything to be out of balance. So then that causes the reactions to flow to the right, which makes more carbonic acid. CO2 gets converted into carbonic acid. And then carbonic acid's a little bit out of balance with its final product at the reaction part that's to the right. So it's going to then separate out and do its own reaction where carbonic acid gives away a free proton, an H+. So it's all about achieving balance. So even when I do these problems on the exam, I like to draw a little set of buckets off to the side and then just, set them up how it was and say, alright, if we add more dots to this one side, how are things going to flow? And that usually does a great job of me being able to visualize what's going to happen there. So we did 11, so we did 12. So let's say, what would happen to the H+, the protons, if the CO2 concentration was decreased? So this was question 13. So let's say we completely get rid of the CO2. This would be like what we did in the lab when we heated up the Sprite and made the soda completely flat. We got rid of all the CO2 bubbles in this situation. So we caused all the CO2 gas to get kicked out and evaporate out basically from the liquid. So now this bucket's empty, but we still have some stuff from these other ones because there was an equilibrium or a balance previously, but we just messed up the system. So now we definitely need to have some atom flow to retrieve balance, right? So let's say we're going to have some sort of the carbonic acid in bucket 2 float over and try to achieve balance. Okay, well, great. So these two are balanced. These two are not anymore. So buckets 2 and 3 need to have some atom flow. So then that's going to cause what would be some H+, the protons, to have to flow in over here to achieve some balance. Great, so it's a little bit more balanced, not perfect. And so then there's going to cause a little bit more chain reaction where some of this is going to have to flow, the carbonic acid that we just made, is going to have to flow back and form some CO2 and water to achieve a full balance. So we initially started with 6 beads over in this third bucket, that's the H+ with the HCO3-, just been referring it to H+ for the protons for convenience. And now we only have 4. So we caused this stuff to decrease as it tried to compensate for having no stuff in this bucket. Okay, so I hope that was a helpful video to describe and visualize what's going on with these equilibrium problems. Have a good day.